Hello, everyone. Today we're very happy to have Jim Propp here to tell us about four tales of the unexpected in undergraduate math research. So go ahead. Oh,
Hello,
and by
everyone.
the way, how would you like people to ask questions?
People should just speak up because it's hard for me to follow a chat at the same time that I'm looking at my slides and pictures. So I will try to put in enough pauses that people can do that. And if I start to go too fast, please remind me to slow down. If there are technical difficulties also, please let me know. So this is work with many undergraduates and non-undergraduates. A few names are Trevor Bass, Carl Bosley, Gabriel Carroll, Henry Cohn, Noam Elkes, Lucas Witkowski, Samira Iyengar, Eric Kuo, Greg Cooperberg, Michael Larson, David Spire, and David Wilson. And the slides for this talk are already on the web, although I haven't updated the most recent version of the slides, but they will be there soon. And since there is a recording being made, I imagine at some point I'll get a copy of the MP4 and I'll put that on my webpage as well. So, does anyone know the three most important words in science? What three words usher in the beginning of every scientific revolution?
Question.
Yeah.
Okay, and then question, match and answer.
What's the question?
I'm asking, is one of the words question? It's like question one of the words. I think question is one of the words.
Oh, no. I'm sorry. This is perhaps a silly question for me to ask because you probably won't get it. But the three most important words in science are, that's weird. Maybe not every scientific revolution, but many scientific discoveries basically announce themselves through something unexpected that happens that means that the previous paradigm just isn't rich enough to accommodate reality, and the paradigm has to expand in some way. So I propose only have seriously, there's stuff in the chat. Let me look at the chat. Oh, this is stuff I've seen before. Oh, Julian Jang has it. Yeah, that's weird, exactly. Yes. So I'm going to propose what I call the E cycle. 1, explore. 2, encounter something you didn't expect. And then 3, explain it. And in math, I would claim that you are often in a situation where you have observed something, but you actually can explain it. You can actually prove that it's true, unlike the sciences where you often don't really know definitively why something is true. But in math, you often do. So the first undergraduate math explorer I want to talk about is Samira Iyengar, now an activist and a dancer, but once upon a time, a math major. And she was looking at some problems I was interested in back in the 80s. Need to close the chat somehow. There we go. Okay. So here are two different shapes that we could look at covering with 1x2 rectangles, also known as dominoes. So you'll notice that both of them have been covered by 1x2 dominoes in a horizontal or vertical position. The one on the left has 12,988,816 tilings of this kind. It's just an 8x8 square. The one on the right is a less familiar shape. It has 32,768 tilings. Those two numbers might not seem very qualitatively different from each other, but the number on the left has some pretty big prime factors. I think 3-digit factors, including 2 and 1-digit factors, prime factors. And if you try to generalize what the formula is for larger and larger 2n by 2n squares, you get this curious trigonometric formula for the number of ways to tile a 2n by 2n square with dominoes. It's not even obvious when you look at it that that's a rational number, let alone an integer, but it is. But 32,768 is a power of 2. And in fact, if you create other pictures on the same plan, where you have n rows on the top of increasing length, 2, 4, 6, 8, 10, etc., up to a row of length 2n, followed by another row of length 2n, and then rows of shrinking length decreasing by 2 until you end with a row of length 2. So there are 2n rows all together. The longest row is of length 2n. You get this fourfold symmetric figure called the Aztec diamond. It always has exactly 2 to the power of n times n plus 1 over 2 domino tilings. The first result was proved by Temperley, Fisher, and Castellane in 1961. The formula on the right was proved by Elkies, Kopperberg, Larsen, and myself in 1992. Very different formulas. The one on the right has a beautiful proof. It's a bijective proof. And what it does is it shows that, well, we know how many bit strings of length 10 there are. There are 2 to the 10th power. And more generally, the number of strings of zeros and ones of length n times n plus 1 over 2 has to be 2 to the power of n times n plus 1 over 2, which is the same as the number of domino tilings of the Aztec diamond of order n, if you believe that formula. Turning that around, you could prove the formula if you could find a one-to-one correspondence, a bijection, between the domino tilings of the Aztec diamond of order n and bit strings of length n times n plus 1 over 2. So that is one of the proofs. But this proof also becomes an engine for generating random tilings of the Aztec diamond of order n, because it's very easy to generate a random bit string of length n times n plus 1 over 2. Just toss a coin n times n plus 1 over 2 times, recording a 0 or a 1, according to whether the coin came up heads or tails. Or if you prefer, use a pseudo-random number generator on a computer. So apply the bijection to that random string of bits, you get a uniformly random domino tiling of the Aztec diamond of order n. When I say uniform, I mean each of the possible tilings has the same chance of being output by your algorithm as any other, just as the coin toss procedure that I described gives the equal probability to all the bit strings of length n times n plus 1 over 2. So now I want to show you what this algorithm does when you run it. And here I have to ask you, can you guys see a 2x2 square with 2 horizontal colored rectangles in it?
Yes.
Yes.
Yeah.
I can't.
Yes.
Okay.
And I can see the arrow.
And you see arrows, right? Is there
Why
someone
is
who's
the
not
Aztec
seeing?
diamond?
I'm sorry?
Why is the Aztec diamond?
What is an Aztec diamond, or why is it called the Aztec
Yeah,
diamond?
why is it called?
Oh, I could not find a name for this shape, so I had to name it. And so it seemed very reminiscent of Native American art. And I needed to find a name that would suggest that, since it wasn't found in European art. And I felt like I should honor the people who first did shapes like that. It was actually more the Hopi Indians than anyone else who liked this particular pattern. But Hopi diamond didn't really sound good. For one thing, there's a famous diamond called the Hope diamond. So it sounded like a really bad pun. But the Aztecs also had shapes like this, and they built sort of square pyramids of a similar plan. So it just seemed like a nice zippy kind of name to give to this. Other than that, it has no real anthropological or other significance. One of the fun things about being a mathematician is if you come up with some new concept, you get to name it. Of course, you have the responsibility to try to choose a good name. Anyway, related to the bijective proof for the formula that I mentioned before is this procedure called domino shuffling. What this procedure does is it takes as input a previous domino tiling of a smaller Aztec diamond of order n minus 1 and just n coin flips, or maybe more coin flips, depending upon how you want to do it. So what it does is it takes a random domino tiling of an Aztec diamond of order n minus 1, and with the aid of additional randomness, generates a random domino tiling of the Aztec diamond of order n. So here is a random domino tiling of the Aztec diamond of order 1. That shape is better known as the 2x2 square. And here's the procedure. You take those rectangles, you put arrows on them, and you slide the rectangles in the direction of the arrows. That frees up some space. And you then cover those two resulting 2x2 squares with either 2 horizontal dominoes with arrows pointing vertically apart from each other, or with 2 vertical dominoes with arrows pointing horizontally apart from each other. So let's do it again. So now I'm going to use some additional randomness. So here I use 2 additional bits of randomness to decide how to fill those 2 2x2 squares. The square on the left got filled with a pair of horizontal dominoes. The square on the right got filled with a pair of vertical dominoes. So let's slide all the dominoes in the directions of the arrows. Whoops, I didn't want to do that. No, I did actually, I did it right. Okay, so all the dominoes slid one step in the direction of the arrow, and that created room for 3 new 2x2 squares, one of which got tiled by vertical dominoes, and the other 2 of which got tiled by horizontal dominoes. By the way, you'll notice that I'm using actually 4 different colors. So I'm going to color dominoes that are horizontal with an upward pointing arrow blue, dominoes with a downward pointing arrow green, rightward pointing arrow red, and leftward pointing arrow orange. So the arrows and the colors convey the exact same information. It's just sometimes useful to see the arrows and sometimes more useful to see patterns of colors. So let's do it again. But I want to point out that we've got a little bit of a problem here, because you'll see 2 arrows pointing towards each other over here and also over here. I don't know if you can see my mouse, my pointer, but you can see 2 vertical dominoes on a collision course and 2 horizontal dominoes on a collision course. So we have actually 3 steps in this procedure. I didn't show you the first step before because it wasn't necessary. But when there are 2 dominoes that have arrows pointing towards each other, we annihilate them with each other. Then we apply the sliding move, where every domino moves 1 step in the direction of its arrow. And then here we have a 3x3 Aztec diamond. The resulting dominoes in the new 4x4 Aztec diamond are going to leave a vacancy that can be covered by 4 2x2 squares. And we use 4 coin tosses to tile those randomly. So let's see how that goes. First annihilation happens, then sliding, and then creation. Okay, actually we had to toss 6 coins, but we could have reused the information in the previous tiling from the dominoes that annihilated each other to get by with only 4 new coin tosses instead of 2. But that's really a nicety. It's simpler for present purposes just to think we use 6 fresh coin tosses to decide what to do. So let's do it one more time and you can see what's happening. So I'm going to annihilate dominoes that are sliding towards each other. Okay. So I'm not going to prove to you that this even makes sense as an algorithm. You could worry that when I do this, there are some collisions or that they don't leave behind 2x2 squares in exactly the right places so that you can tile them randomly using coin tosses to decide whether to use horizontal dominoes or vertical dominoes. But I invite you to notice that it always seems to work. And I make an additional claim that I won't prove, which is that if you follow this procedure, what you see at each stage is a uniformly random domino tiling of the Aztec diamond of that order. So you're starting to see segregation of colors at the top and bottom, and to a lesser extent at the left and right of the picture, where these things line up. Let's do 10 iterations at once. That went by so fast you couldn't see it. But you're seeing more of that color segregation. Let's do another 10. Now you can't even see the arrow, so that's kind of why I wanted to use colors, because at this point you just can't see arrows. You can see colors, and we can keep going and going, going. So Samira Iyengar was the first person to do this, and she showed me the picture, and we both noticed it was kind of strange that there was all this orderly behavior in the corners of the Aztec diamond and random behavior in the middle, and the boundary between the random stuff in the middle and the orderly stuff in the corners appeared to be a circle of all things. That was surprising, and that was the first unexpected thing. And it was found by an undergraduate programmer who worked for me when we were both at MIT. This was through MIT's Undergraduate Research Opportunities Program. So this result is now called the Arctic Circle theorem. The motivation there is that there's sort of frozen dominoes in the 4 corners. Never mind that on Earth, the North and South poles, there's just 2 poles. Here there are sort of 4 poles, north, south, east, and west, where things are frozen. whereas in the middle of the tiling, things are hotter, meaning more random. So why is it a circle? Well, I can prove it, and there have been a lot of proofs since my original proof of this, but I don't really have a good intuitive answer to why it should be a circle. But there's a beautiful video made by a YouTuber named Mathologer. So if you want to know more about the Arctic Circle theorem, go to his video, The Arctic Circle Theorem. I've been talking a lot. Any questions before I go on to part 2?
Wait, so you said you don't have a good answer to this, but like, doesn't mean that you don't have a good intuitive answer, but like you have like an answer?
Yes, I have an answer and it's a proof. But what I mean by a good answer is an intuitive answer that would explain why the circular symmetry of the circle suddenly appears in this seemingly asymmetrical situation. I mean, it depends on what you mean by a circle in the sentence, why a circle? If the question is, why should it be an algebraic curve satisfying a quadratic equation? I sort of have a good answer for that. But why, but why isn't it an ellipse? Why does it have this extra symmetry? It's still a little unclear to me. But I think good answer is a highly subjective thing. And you've probably all been in situations where you're in classrooms where everybody understands something or says they do, and you're confused because you're thinking about things on a deeper level than they are. That can be a very frustrating situation to be in when your teacher doesn't understand that the reason you're confused is you're trying to get underneath things that other people may not see. So I'm very rigorous about what I want in an answer. And yes, I can prove this in a bunch of ways, but I'd still like to see a simpler, more transparent proof, because the proofs I've seen have a lot of steps, and somehow the intuition leaks out along the way. Okay, let me go on to the next explorer, Eric Kuo, also at MIT. I'm going to have to give you some more background to explain what he did. So, although the Aztec diamond got named by me, after I named it, I found out that some physicists had already basically invented the same shape. But they didn't give it a name, and they didn't prove the phenomenon, although they'd conjectured it. It wasn't interesting to them to try to prove it, so they just observed it and said, seems to be true, but it's not interesting to us, so they moved on. They thought in terms of dimers rather than dominoes, so let me show you what a dimer is. A dimer is also called a perfect matching. So you can see a whole bunch of dashed lines and solid lines joining these black and white dots. Ignore the other lines at this moment, the ones that form a domino tiling. If you just have these black and white dots and all the lines that join them up, that forms a graph. A graph theorist would say that it's sort of dual to the Aztec diamond picture that I was showing you before, which was made of squares. Here we have a dot in the middle of each square. And what we would call a domino tiling before is now a way of pairing up every black dot with a white dot. And you can go in the reverse direction. If you have a way of pairing up every black dot with a white dot that's adjacent to it in this graph, you can turn that into a domino tiling. So there's no serious difference between them except the cosmetic one. So physicists were interested in what they called perfect matchings of graphs, collections of edges with the property that every vertex belongs to exactly one of the selected edges. So it turns out there's a relationship between perfect matchings and determinants. These guys, Grensing and company, were following up on work in the 1960s by Temperley, Fisher, and Castellane. Those were the people I mentioned before who counted the number of ways to tile a 2n by 2n square with dominoes, who showed that perfect matchings of planar graphs could be counted using determinants of matrices. So let me say here what the determinant of a matrix is. So you've got an n by n array of numbers. We'll have two subscripts, I and j, each of which goes from 1 to n. So I and j both vary independently from 1 to n. And what we do is we take all the one-to-one and onto functions from the set of indices 1 through n to itself. And we take a sub 1 comma pi of 1 times a sub 2 comma pi of 2 dot 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 and so forth, and multiply all those entries together, which in the case of a matrix just means you circle a bunch of entries. So that you circle one entry in each row and one entry in each column, n rows and n columns. So choose n entries so that they jointly represent every row and every column exactly once. Multiply those matrix entries together. multiply by a magic sign, which is often written as -1 to the power of the number of inversions of pi. I won't go into what the number of inversions is, because it's not going to be important for today. And then you sum that over all the permutations, all the functions from the numbers from 1 to n to that set itself. So that is one way of defining the determinant of a matrix. I'll show you what the case n equals 2 looks like in a minute. I will mention that in the case n equals 0, what is a 0 by 0 matrix? I mean, I know what a 1 by 1 matrix is. It's just a number that you don't think of as being a number. You think of it as being the sole entry of a 1 by 1 matrix. The determinant of that matrix is just the number you put into the 1 by 1 matrix. Turns out it's convenient to think about 0 by 0 matrices too. But the determinant of a 0 by 0 matrix is not 0. It's 1. You've heard about this before, like 0 factorial. You'd think it's 0, but it's more natural to define it to be 1. Number to the power of 0 is also equal to 1. So this is another fact in that direction. It's not so much a mathematical fact as a fact about what turns out to be a convenient definition to make the theorems we know and love easier to state. So it turns out you can think about pi, this bijection, as a perfect matching of the sets of rows with a set of columns. So let me show you what it looks like in the case where n is 2. So at the bottom, you see a 2 by 2 matrix with entries A11, A12, A21, and A22. And you've probably seen that the formula for the determinant of such a matrix is A11 times A22 minus A12 times A21. But another way you could think about it is taking perfect matchings of a graph that has 4 edges. There is an edge that goes from vertex 1 on the left to vertex 1 on the right. And we assign that edge the weight a sub 1, 1. And we have an edge from vertex 2 on the left to vertex 2 on the right. And we assign it weight a2, 2. And those two edges together form one of the perfect matchings of this graph. But there are 2 more edges, which also taken together form a perfect matching of this graph, namely an edge from vertex 1 on the left to vertex 2 on the right, whose weight is a1, 2, and conversely, an edge from vertex 2 on the left to vertex 1 on the right, and that has weight a2, 1. So you can say that the weighted perfect matchings have weights a11, a2, 2, and a12, a2, 1. And if you sum the weights of the matchings and throw in a minus sign, you get the determinant. And by the way, I'll often write the determinant with these vertical goalposts that you've probably seen before. So that already tells you there's something similar about perfect matchings of graphs and determinants. But you can't just write the number of perfect matchings of any old graph as a determinant. It has to be quite often a planar graph. That is a graph you can draw without crossings. Unlike this graph that I've shown here, I haven't shown you all 4 edges at once, but you see those 2 diagonal edges cross each other. But if you have a graph where no edges cross each other, then it turns out if it's a bipartite graph, meaning there's a left side and a right side and all the edges connect something on the left to something on the right, or you could divide the vertices into 2 sets, black and white, and all the edges go in a black vertex to a white vertex. In such a case, if it's planar, you can always write the number of perfect matchings as a determinant. And Castellane figured out how to do this. So meanwhile, while physicists were doing this, quantum chemists also got interested in perfect matchings of graphs because of their relevance to what's called aromaticity of benzenoid molecules. So benzenoid molecules smell. And one reason they smell is because of the quantum chemistry, which is this resonance phenomenon. And the resonance phenomenon you might have learned in a chemistry class is related to this kind of ambiguity of which of the bonds in benzene are single bonds and which are double bonds, the kind of ambiguity that manifests itself on the quantum level through resonance. And that's because this graph has 2 perfect matchings. So properties of benzenoid molecules are related to the number of perfect matchings the associated graphs have. Because it's already almost 8:30, I think I'm going to skip over this one, except to say that you see on the right an example of a perfect matching of a honeycomb graph, which is kind of like one of these benzenoid type molecules because it's made of this characteristic ring of 6. But pure mathematicians got interested in this stuff as well. And there you can see a sort of bijection between a perfect matching of a graph and a tiling of a hexagon with rhombuses, where you can recover one from the other For instance, here, if you look at the picture on the right, the very top edge is marked in bold, meaning that's one of the edges in the perfect matching. And you'll see over here in the middle picture, I've got a rhombus that's pointing from left to right. But I'll have to skip over that. Anyway, this is all still just background for what Eric Quo did. There's this formula often called Lewis Carroll's identity or Charles Dodgson's identity, because the mathematician and children's book author actually figured this out independently and made interesting use of it. It's a relationship between 6 determinants. If you've got an n by n matrix M, you can form what are called minors of the matrix by choosing a bunch of rows and columns to form a submatrix. So if you take the northwest rows and columns, so you ignore the bottom row and the rightmost row, you get an n minus 1 by n minus 1 submatrix that I'll call M sub NW, NW for northwest. Or you could just take the n minus 1 northernmost and easternmost rows and columns to get M sub NE, and likewise for SW for southwest and SE for southeast. And you can throw out the first row, the last row, and the first column, the last column to form a central n minus 2 by n minus 2 submatrix, which I'll call M sub C. And this 1841 identity asserts that if you take the determinant of the n by n matrix and multiply it by the determinant of the n minus 2 by n minus 2 matrix, the result is equal to the difference between two other similar products, the determinant of M sub NW times the determinant of M sub SE, and the determinant of M sub NE and the determinant of M sub SW. So let me give you an example of this. So here's a 3 by 3 matrix, M, and there's the northwest, northeast, southwest, and southeast matrices, and the central matrix is going to be the 1 by 1 matrix whose only entry is 5. So this identity claims that this equation marked with a question mark is true. Now, I don't know if you know that much about determinants, but when one row of a matrix can be written as a combination of two other rows, the determinant is always 0. And that's the case here because the middle row is equal to the average of the first and last row. So that 3 by 3 matrix has determinant 0. The 1 by 1 matrix has determinant 5. And I'm going to have to rush through this, but if you use the formula for the determinants of 2 by 2 matrices, sure enough, the right-hand side of this equation also gives you 0. 0 equals 0 is not very interesting, but here's what Dodgson realized. He realized you could turn this into a procedure for computing determinants recursively. So he divides both sides of the Desnanot formula by the determinant of the central matrix, and he gets a procedure. I'll show you how it works. Suppose you want to take the determinant of this 4 by 4 matrix. Take each 2 by 2 subdeterminant and arrange them in a 3 by 3 matrix. So we're always taking 2 consecutive rows and 2 consecutive columns, which form a 2 by 2 matrix. Take its determinant. That gives us these numbers. Now do the same thing again, but you have to divide those 4 determinants by 2, 3, 3, and 6, respectively. That's the M sub C that we have to divide by. And now we do a similar thing here. Take this 2 by 2 matrix, compute its determinant, you get 3. But we have to divide by this 3, so we get 1. So that is Dodgson condensation, a way of evaluating determinants. So here, finally, I can tell you what Eric Quo did. He found a graph theory analog of this identity and a method of graph condensation for counting perfect matchings of many planar graphs by peeling off the boundaries of the graphs, getting smaller and smaller graphs, just as we did with determinants there. So here is his graphical Desnanot-Jacobi identity. Because I'm running late, I will skip saying anything more about it. Here's what it looks like in action. So here, when you apply it to one of these Aztec diamonds, here it's the Aztec diamond graph that the physicists preferred. You just cut off a whole bunch of edges along the top and bottom, or left and right, and you reduce the problem to counting perfect matchings of a smaller Aztec diamond graph. So you can get a nice recurrence relation and you can solve it, and it's a beautiful way to prove the formula. Or here's an application to one of these honeycomb graphs. And again, I'm going to have to skip over that because here's the middle of the talk and it's already 8:33. So I want to talk about what Mills, Robbins, and Rumsey did. They did something very playful. At least I think it was playful. They may have had a serious reason for doing this. And because they worked for the National Security Agency, they couldn't explain all the reasons for all the problems they worked at. Some of it may be classified. but it was deemed that this spin-off of their work was sufficiently inessential to national security that they could publish about it. So they were looking at Dodgson condensation, and they put in a new variable called lambda. So the classical determinant is the lambda determinant when this new parameter lambda is -1. So in the case of 2 by 2 matrices, this looks a lot like the permanent of a matrix, where you change the minus to a plus, but for 3 by 3 matrices, it's quite different. So let me describe to you what Mills, Robbins, and Rumsey did. It's a procedure for reducing a large array, square array of numbers to a single number, kind of like Dodgson condensation, but with a different recurrence. So the initial conditions, which I haven't shown you here, you should imagine that there's a 5 by 5 matrix of all ones. Sitting on top of that, in a square pyramid form, is a 4 by 4 array of these numbers whose superscripts are ones. You can see the superscript's 1 there. And then sitting above that, superscript 2, and sitting above that, superscript 3, and sitting at the apex of the pyramid, a superscript 4, sub 4, comma 4, that is going to be the lambda determinant of this array, the 4 by 4 array of numbers. And if lambda is -1, it's just the ordinary determinant. But so we have a sort of hidden basement level, which is all ones. And then the bottom level that we see is the numbers that basically are analogous to the entries of a matrix. And then this determinant, I'll skip explaining how the notation works, but it's just like Dodgson condensation, except instead of subtracting here, we're adding plus lambda. So if lambda were -1, this would just be Dodgson condensation, but we're doing something different. So I said before that if you take the lambda determinant of a 2 by 2 matrix, it's just A11 times A22 plus lambda times A12 times A21. It's more interesting if you look at the lambda determinant of a 3 by 3 matrix. You get 6 terms which look kind of familiar. They're the 6 terms in the expansion of a 3 by 3 determinant. But then you get this oddball term. It goes away when lambda is -1 because that coefficient lambda plus lambda squared becomes -1 plus +1, which is 0. But check out what we've got here. It's no longer just circling a bunch of entries such that you have 1 in each row and 1 in each column. But it is raising each of the fundamental variables in the bottom layer of this pyramid to a power that's +1 or -1. And so they said, that's weird. Let's do more levels and see what we get.
Hey, by the way,
Yeah.
I saw one coefficient, you took its inverse. Does that mean you take 1 divided by it? Or
Exactly.
what if that
Which could raise
coefficient is?
if the entry
what
is
is-
0, yeah, that can create problems. So I'm
Ah.
skipping over the whole dividing by 0 issue here. Yeah.
Okay.
So let's rewrite these patterns of exponents in matrix form. So now we've got one oddball matrix. So here's the first 6 matrices have a 1 in each row and a 1 in each column. Here we don't have that, but all the row sums are equal to 1, and all the column sums are equal to 1, just like in the other 6 matrices. And the 1s and -1s alternate in any given row or column where you have a -1. So those were dubbed alternating sign matrices, and they wondered how many there were, and they conjectured a formula, but they couldn't prove it. And a lot of people got really frustrated. In 1991, Robbins wrote, "These conjectures are of such compelling simplicity that it is hard to understand how any mathematician can bear the pain of living without understanding why they are true." Well, it finally got proved. But they also wrote about compatible pairs of alternating sign matrices. Because remember I mentioned that sub-basement of all ones? Let's give them variables too. So now I've got 2 rows of initial variables. There's the sub-basement, and that's B for basement. And then there's the ground floor, which is A. And if you look at what the lambda determinant, generalized lambda determinant of that pattern of initial variables is going to be, you find it's given by pairs of alternating sign matrices that turn out to be domino tilings of Aztec diamonds in disguise. So here is a compatible pair of alternating sign matrices. You do some algebraic operation on them that I can't talk about. Then you join up the ones where the numbers are adjacent. So for example, you don't join the 5 and the 8, but you do join the 7 and the 8. Lo and behold, you get a domino tiling out of this.
No! The Aztec diamond has returned.
Yeah. Okay, third surprise was Ben Wieland, who was looking at a different way that Aztec diamonds make themselves felt, because they have many different avatars in the combinatorial world. So physicists were looking, let me skip ahead to this picture. So you'll notice that in this picture, I've got a bunch of edges that form closed paths that begin on the boundary and end on the boundary. Like there's one that joins 1 to 3, one that joins 5 to 15, ones that join 7 to 9. So the fully packed loop model is a collection of edges of what kind of graph? Well, it's an n+2 by n+2 grid graph with 4 corners removed, consisting of n squared internal vertices and 4n external vertices, joined to the internal vertices by 4n external edges, as shown here for n equals 4. And what we're looking at is collection of edges such that each internal vertex belongs to 2 edges in the collection, while the odd-numbered external edges are required to be present, and the even-numbered external edges are required to be absent. So 1 is on an edge to the interior, 2 isn't, 3 is, 4 isn't, 5 is, 6 isn't, and so forth. It turns out that if you look at this, there's 2 kinds of paths. There are going to be paths that join the boundary to itself, or there could be paths like what you see in the middle here, which form an actual loop, which is what gives the fully packed loops model its name. But these loops and closed paths can't cross each other. And it turns out that they are in one-to-one correspondence with alternating sign matrices. But what they noticed, what some students noticed, is this strange fact. Look at vertex 1 and vertex 3. That's in the top row, the left vertex and the right vertex. There's one configuration in the fully packed loop model that joins them to each other. Oh, here's another one, 2, and here's another one, 3. So there are 3 of these fully packed loop states that join vertex 1 to vertex 3. How about vertex 3 to vertex 5? This one joins vertex 3 and 5, and so does this one. Oh, but so does this one. It's just kind of indirect. It goes into the interior a bit more deeply. So there are 3 FPL states in which vertex 3 is joined to vertex 5. Also, vertex 5 joined to vertex 7, there are 3. Vertex 7 to vertex 9, there are 3. So what Ben Wieland and other UROP students found is that if you take any pairing of the odd numbers 1, 3, 5, etc., up through 4n minus 1, and if you add 2 to that pairing, so instead of pairing 1 with 3, you pair 3 with 5, or instead of pairing 1 with 5, you pair 3 with 7. So increase it by 2, or increase everything by 4, or increase everything by 6, modulo 4n, so that we end up with numbers between 1 and 4n minus 1. That's going to give a totally different pairing of the points on the boundary. But the number of such states is going to be the same. And this is really weird because squares aren't round. Again, we can ask the question, why should there be cyclic symmetry of the kind you see from a circle with a model that's based on the square? So let me just plug in my laptop because it's running low. So I'm going to have to skip the nuttier still, but you can look at the notes online. The fourth cool thing that a student found was David Spire, who did some work on what are called Somos sequences. Let me just check the chat here. Wait, what did you do in Euler Circle class in winter?
That was about Dodgson condensation.
Oh, cool. I think it's still an open problem how to really implement it efficiently, given that there can be entries equal to 0. As far as I know, nobody's fully worked out that problem. There are kludges, but I don't think that story is finished. Anyway, in the 1980s, Michael Somos introduced a bunch of surprising integer sequences, including this one. Okay. You've seen Fibonacci numbers. It's not surprising that each term of the Fibonacci number is a whole number because it's the sum of 2 whole numbers. This recurrence is different. Look at that recurrence. The nth term is equal to the n minus first term times the n minus third term plus the square of the n minus second term, all divided by the n minus fourth term. So for example, if we didn't have the last term 1529, the way Somos would compute it is you take the term before it, which is 314, multiply it by the term that's two terms before that, which is 23, increase that amount by the square of the intervening term, which is 59, and take that sum and divide it by the term that comes even before that, which is the 7. Okay? But hold on a minute. Why should this be a whole number? Why should 314 times 23 plus 59 times 59 be a multiple of 7? It's totally unclear. And why does this fortunate divisibility behavior continue for the next term and the next term and for infinitely many terms? This is just a very surprising sequence in the sense that even the fact that it gives you an integer sequence given the defining recurrence relation requires, some explanation. But the mystery gets deeper. Suppose instead of starting the sequence with 1, 1, 1, 1, we start it with W, X, Y, and Z. Well, we get the next best thing to being an integer. The subsequent terms are what we call Laurent polynomials in the variables W, X, Y, and Z. So here's an example of a Laurent polynomial, xz plus y squared over w. It's a Laurent polynomial because you can expand it as a sum of what are called Laurent monomials, where you have a bunch of variables raised to powers that are integers. What distinguishes a Laurent monomial from a monomial is that in monomials, you have to use non-negative powers of the variables. But in Laurent monomials, you're allowed to have negative integer powers. So I don't know if anyone's talking about cluster algebras, but I think someone is, and this is kind of at the heart of the magic of cluster algebras. But you should have a sense of deja vu, because we already sort of saw Laurent monomials cropping up when we did Dodgson condensation and lambda determinants. So that recurrence involved dividing one complicated polynomial with lots of variables by another slightly less complicated one. But we always ended up with a sum of Laurent monomials. So this is deeply weird. The weirdness and the sense of deja vu can be heightened if instead of looking beyond Somos 4 to Somos 5, Somos 6, etc. By the way, the magic ends at 6. Somos 7 isn't a sequence of integers. Let's go the other way. Let's go back to Somos 3 and all the way back to Somos 2. One natural definition of Somos 2 gives us this recurrence. A sub n equals a sub n minus 1 squared plus a sub n minus 1 squared over a sub n minus 2. And when you solve that recurrence, it's very easy to show you get 2 to the power of n times n plus 1 over 2, which is the number of domino tilings of the Aztec diamond of order n. What's the connection here? Might the Somos 4 numbers be counting perfect matchings in some infinite family of growing planar graphs, analogous to but different from the Aztec diamond graphs? So in pursuit of an answer, I found a kind of tilted variant of lambda Dodgson condensation that gave rise to Somos-ish multivariate Laurent polynomials with lots of variables. Now remember, Dodgson condensation starts out with n squared variables, because you start out with the n squared entries of an n by n matrix. So I found a sequence of Laurent polynomials, kind of like lambda Dodgson condensation, that again has about n squared variables, and also, as in Dodgson condensation, has the property that if you replace all variables by 1, you get, I'm sorry, I shouldn't have said what I just said. It has the property that replacing all the variables by 1 gives the nth term of the Somos 4 sequence. Now that doesn't seem to cast light on what these Somos numbers are counting. But in fact, these Laurent polynomials empirically seem to be strongly monic in the sense that all coefficients equal 1. Now, if you've got a polynomial with all coefficients equal to 1, asking how many terms there are is equivalent to asking what do you get when you replace all the variables by 1, which is equivalent to asking what's the value of this polynomial when all variables are equal to 1, which is just going to be the nth term of the Somos sequence. So the number of terms in this horribly complicated multivariate Laurent polynomial is the nth term of the Somos 4 sequence. So in a sense, I had an answer. What secret combinatorial objects does the Somos 4 sequence count That answer is it counts terms in these multivariate Laurent polynomials. But that was a very unsatisfactory answer because it wasn't proved. And more importantly, the combinatorics is sort of hiding behind the algebra. We've got this algebraic engine that generates these Laurent polynomials. But remember, with Dodgson condensation, we were able to identify alternating sign matrices in a purely combinatorial way as matrices of zeros, ones, and minus ones, with the property that every row sum is 1, every column sum is 1, and the entries alternate in sign. And likewise, when we looked at compatible pairs of alternating sign matrices, we had a very combinatorial description of those in terms of domino tilings of Aztec diamonds. So I didn't want to see an algebraic answer to the question, what do these numbers count? I wanted a combinatorial answer. But one might hope that there's somehow a grammar lurking in the pattern of the exponents of all these variables. And that if we look at them hard enough, we'll figure out what's going on. Well, David Spire, in 2001, participating in a program that I called REACH, or Research Experiences in Algebraic Combinatorics at Harvard, managed to reverse engineer some graphs by looking very hard at those Laurent polynomials and saying, what sort of monomials can occur and which ones can't occur? How are the exponents related to each other? And he was able to do this in such a way that Quo's graphical condensation algorithm turned into the Somos 4 recurrence. So remember, Quo condensation is a recurrence relation with 6 terms. It says this times this equals that times that, plus or maybe minus that times that. And Somos 4 is something of the same kind. So this resemblance was turned actually into something airtight mathematically by David Spire. And so here is the answer, or here at least is a glimpse into the answer combinatorially. The terms of the Somos 4 sequence, which you see at the top of the t-shirt design, count perfect matchings of these graphs. And it's not clear what the rule is, but you can sort of see patterns for how these shapes are made. And it's not too hard to describe them. And it turns out if you apply Quo condensation to these graphs and write down what it really means, it turns into the Somos 4 recurrence. And it was Trevor Bass who created this picture. So I've given you now a glimpse into my work and a glimpse into the role that undergraduates have played. And one thing I like about the kind of work that I do is you really can get your hands dirty playing around with things without learning a lot of abstract and very important mathematics, which you would do well to learn during your undergraduate years, because just like learning a first language is easier, learning a second language is easier when you're a kid, learning abstract math, I think, becomes harder as you get older. So when I say I love mathematics, I love combinatorics for its concreteness and accessibility, I would be sad if that remark made any of you decide you were never going to learn algebraic geometry or ergodic theory or anything like that, because the more different types of mathematics you feel comfortable with, the more resemblances you can find between seemingly different fields of mathematics. And we've seen a little bit of that here, where things done by physicists and things done by combinatorialists turn out not just to resemble each other, but to have deep mathematical connections. And the more different kinds of math you know, the more new connections you can find, and the more important mathematics you can do. But if you want to get your feet wet doing mathematics to find out if the frustration of doing math fits your temperament, because math research can be a very frustrating endeavor. You spend most of your time being stuck, and then you have a brilliant idea, and then you push that idea to the max and you get a whole bunch of results, but then you're stuck again. You need to find another idea. So I happen to be okay with that kind of frustration. But a good way to find out if the math research life is for you is to get your feet wet in research problems pretty early on. And combinatorics is a great place to do it, because pretty quickly you get to the frontiers, you can understand the questions without having to, take a graduate course. And then sometimes you can solve a problem with advanced techniques, but sometimes you can use very elementary techniques in a new way, or you can invent new techniques for solving problems, as Eric Quo did. So that is my advertisement for this style of research. Oh, and here's the back of the t-shirt. So you can see the name of the group, REACH, at the top. And there are the 7 perfect matchings of the Somos 4 graph of size 7. So that's all I got. Thank you very much for listening.
thanks for a great talk. So, are there any questions?
I see someone's chatted something in the chat. Let me read that. Oh yeah, that's a link. Yep. So that's a slightly old version of the article. So you can look at that now, but please don't download it because I've got a slightly updated version on my laptop, which I will put to the web before I go to bed tonight. So you'll be able to see that. And Simon, are you planning on putting the MP4 on the web someplace?
Yeah, I'll have it up tonight or maybe tomorrow, and then I'll send you a link.
Great.
Yeah, so any questions? That's a little surprising. But anyway, okay, so thanks. I guess that's all for this part of the talk. So let me stop this recording.